Hey Harris, I hope you're okay. No starter, we're just going to jump straight into this. We're going to do some excess percentage yield and enthalpy of combustion consolidation. So I'm going to do one excess question, couple percentage yield questions and a couple of enthalpy combustion questions just to consolidate because it is still part of Unit 3. And enthalpy combustion, I know a lot of people struggle with that, so I've kind of altered it just a wee bit. I've added a wee bit in one of the steps, so hopefully that helps. But let's just start. So the first thing we're going to do, again, I want you to start creating the notes that I'm creating. So excess, and the first question is going to be if 4.4 grams of iron 2 sulfide sulfide, yeah, so if 4.4 grams of iron 2 sulfide was added to 160 centimetre cubed of 0.5 mole per litre hydrochloric acid, okay, show by calculation which reactant is in excess, and then what mass of iron chloride is made. Okay, so I'll write the equation for us. So FeS plus 2 moles of HCl, and that goes to FeCl2 plus H2S. Okay, so that's the question. I'm going to write the answer in red. So this is what we do. Now, first things first, with all calculations, we write what we know. Okay, that's always your number one. So mass, we know, is 4.4 grams. Yeah, we know the concentration is 0.5, and we know the volume of hydrochloric acid is 160, but we divide by 1,000 because we want to convert it into litres, so that's 0.16. Okay, now the question, the second part to this question, okay, we're trying to work out the mass of iron chloride. Okay, so the first part we use the reactants, second part we're going to use the product. So with any excess question, we do the exact same thing. We split the page into 3, and it's the mole ratio in the middle, and it's the mole ratio between the iron sulfide and the HCl, which is 1 to 2. Okay, so iron sulfide on the left, HCl on the right. So we need to work at the GFM. So for sulphur it's 32.1, for iron 55.8, I'm sure if that is, and then we add that up, that will give us 87.9. Okay, because we're given a mass, we've got the GFM, we use M over GFM, so that is 4.4 divided by 87.9. And if we do that in our calculators, we are getting 0.05 moles. Okay, this goes up here, so 0.05, arrow, underneath the arrow needs, okay, so 0.05 needs, it's a 1 to 2 ratio, so times it by 2, that's 0.1. Okay, then we do the same for the HCl. So because we've got a concentration volume, we use N equals CV, so that is 0.5 times 0.16, I can do that in my head, and that will be 0.08 moles. Okay, bring that in, 0.08 moles needs 0.04. Now remember, with excess questions, like I said, you always focus on the top right and the far right. Okay, now just to clarify, the top right, the far right, that's what we have. And the far left, that's what we have. Okay, so the two ones on the side, that's the number of moles we have. This one in the middle, the top right, where the arrow's pointing, that's what we need. Okay, then we write our sentences. Okay, I'm just going to use a different pen just so it stands out. So we need 0.1 moles of HCl. We have 0.08 moles of HCl. So we need 0.1 moles of HCl. We have 0.08 moles. So because that's a lower number, that means the HCl is limiting. Okay, so by default, if the HCl is limiting, that means that the iron sulfide is in excess. So we've answered the question. Okay, now for the next part, calculate the mass of iron chloride. Remember what I said. When we're taking it forward, we focus on the limiting. Yeah, we don't do anything else. We focus solely on the limiting reactant. So we bring that down. Okay, so we've got 2 moles up here of HCl, and that gives us 1 mole of iron chloride. So that's a 1 to 2 mole ratio. Now, here we need to put what we have. Okay, now we don't put 0.05 because that's what we have of iron sulfide. Yeah, we're after hydrochloric acid, so we have 0.08 moles. Okay, we have 0.08 moles of HCl. It's a, it's not a 1 to 2, it's a 2 to 1 mole ratio, so that's 0.04 moles. Okay, iron chloride, we can do the GFM. 1 chlorine's 55.5, so 2 will be 71, and then iron we already know is 55.8, so that will add up to 126.8. Okay, then we just need to work out the mass. So mass equals N times GFM, number of moles 0.04 times 126.8, and if we sub that into our calculators, so 0.04 times 126.8, that is 5.072 grams. Yeah, and that's it. That's how we do excess. Right, next one we do then is we do percentage yield. Now I'm going to do 2 percentage yield questions, and that's because you can get asked 2 different types of percentage yield. You can be asked to work out the percentage yield, and then you can be asked to work out the actual yield. Okay, so first question, we'll keep it simple. 0.112 grams of hydrogen is reacted with excess, so that tells us the hydrogen's the limiting one, so with excess iron oxide, okay, 0.745 grams of water is produced. And finally, the question wants you to calculate the percentage yield. So this is the equation here. Fe3, that is, Fe3 plus 4H2, that goes to 3 moles of iron plus 4 moles of water. So, as usual, we change to red. And again, first things first, doesn't matter if it's an excess question or percentage yield question, we write what we know. Okay, so what we know is we've got 0.112 grams of hydrogen, and we have 0.745 grams. Okay, now I want to highlight this. This here, yeah, That's what's being produced, okay? So that is what we have actually made. So that is our actual yield, okay? That's the actual yield. Now, what we need to do, if we use that, we need to work out what we would have got, what we would get theoretically, okay? So, we split our page, as usual, into 3 mole ratio in the middle, and it's a mole ratio, of course, between hydrogen and water, and it is a 4:4, which simplifies down to a 1:1. Okay, so hydrogen on the left, water on the right. So hydrogen's got a GFM of 2. N equals M over GFM, so that is 0.112 divided by 2, and we are getting 0.056 moles. Yeah? Bring that in. So 0.056, 1:1 would give us 0.056. And then we're working out the mass, but let's do the GFM quickly. So that's 16, 2, that adds up to 18. So M equals N times GFM. So bring the moles over, so that's 0.056 times 18. And we're getting 1.0. Oh. Let's see, do it on our calculators. I'm doing that in my head. 1.008 grams. Okay, so I'm going to highlight that a different colour. Now, that is a theoretical yield. That is, if this reaction went perfectly, yeah, there was no loss of any reactants, there wasn't any impurities, anything like that. If this went perfect, we would get 1.008 grams. So that's a theoretical yield, okay? But we actually, in this reaction, got 0.745 grams. So we need to work out the percentage yield. And again, you can get this straight from the data book. I'm simplifying it. Yeah, just makes it easier. Actual over theoretical, times that by 100. You can simplify it as well. Yeah. So our actual was 0.745. Our theoretical was 1.008. Times by 100. A lot of people forget to times by 100. Yeah. Times by 100. So let's do that. 0.745 divided by 1.008, times that by 100, and our percentage yield was 73.9%. So that's quite a high percentage yield. Water, that would be I don't know if it is a desired product, but you could work out the atom economy of the water if you want. Yeah. But anyway, let's go on to the next question. So B, 40.8 grams of C6H6O3 produces a 39% yield. Okay, so it's a wee bit of a twist to this question. Calculate the mass of water produced. Okay, if we've got a yield of 39%. Right, here is the equation, so it's C6H6O3 plus 6 moles of oxygen, and that goes to 6 moles of carbon dioxide plus 3 moles of H2O. So I'll change to red. And again, as usual, it's the same thing. Write what you know. Okay, so we know from this question we've got a mass of 40.8 grams of C6H6O3, and we are trying to work out the mass of water. Now, that mass of water, that's the actual yield. Yeah, that's what we would have actually got. And also, we know that the percentage is 39%. Okay, so split our page as usual, and we have the mole ratio. Mole ratio between what? Well, it's going to be the C6H6O3 and the H2O, and that is a 1:3. Okay, so C6H6O3 on the left and H2O on the right. So if we do the GFM, 3 times 16, that's 46. 6 times 1, 6. 6 times 12, 72. And if we add all that together, we're going to get 126. Okay? Number of moles equals mass over GFM. So that is 40.8 from the question, divided by the GFM, which is 126. So we do that in our calculators, 40.8 divided by 126, that would be 0.324 moles. Okay, transfer that in, 0.324, times that by 3, we're going to get 0.972. And finally, we need to work out the mass. So the GFM of water is 18. The mass, N times GFM. Bring the moles in, so that's 0.972 times 18. Okay, so 0.972 times 18, and we're getting 17.496 grams. Okay, now I'll highlight that orange, just like I did in the last question. That there is our theoretical. Now, that's if the reaction went at 100%. So at 100%, we're getting that. Okay, now the next part, this is just as easy. So we went over this in class, but at 100% yield, we get 17.496 grams. Yeah, at 100%, that's what we get. Now, the question's asking for 39%. So 39% is X, because we don't know it. Okay, so what do we do next? We cross multiply. So X equals 39 times 17.496 divided by 100, and if we do that, times 39 divided by 100, we are going to get 6.82 grams. And that's it, that's percentage yield. Yeah, nice and easy. Nice and easy. Right. Next one is enthalpy of combustion. Now I know a lot of people have difficulty with this. Understanding, where do we match the GFM up to? What does EH mean? Is that the GFM? Like, and so on. So we're going to do it just like what we normally do, but I'm going to add one extra step in, okay? And hopefully this will help, okay? So question A, I want you to calculate, now I'm lazy, I'm just going to write the EOC, calculate enthalpy of combustion of methanol, okay? Now you should know that methanol is CH3OH, but I'll be nice enough to give you it. So calculate enthalpy of combustion of methanol when 1.2 grams of it is burned. Okay, now we need a wee bit more information obviously, so the energy released from this heats 650 centimetre cubed of water from 22 degrees Celsius to 32 degrees Celsius. Okay, so we're going to do this in red. So with enthalpy of combustion, we're splitting our page in two. Okay, that doesn't change. Yeah, our headings, we're going to put EH equals CM delta T and EOC for enthalpy of combustion. Yeah, and now remember the mass of 1 mole equals the GFM. You can write that if you want. Now, you need to work out what side you want to start on. Okay, now we have enough information here to work out EH, so that's where we're going to start. Okay, so if we do a wee sidebar, EH we don't know, C, because it's water, it's always 4.18. M is the mass of water. Okay, it's the mass of water, not the mass of what's burned. Don't make that mistake. Yeah, it's the mass of water, and we need to convert it into kilograms, and we divide by 1,000, so that's 0.65. And then delta T is the change in temperature. It's went from 22 to 32, so the change is 10. So this is going to be 4.18 times 0.65 times 10. And if I do that on my calculator, 4.18 times 0.65 times 10, we are getting 27.17 kilojoules. Now, I'm going to start colour coordinating stuff. This is going to be pink, and you'll see why I'm colour coordinating it. So this will be pink. Now, remember, this is EH is the only one that can cross over from either side. So if we worked out the EH there, that could come over. If we worked out the EH there, that can come over. So the next thing you always want to do is work out the GFM. But before we do that, I'm going to create this next step here. Okay, and I'll do it in a different colour. I'll do it in black so it stands out. Now, this will help, or it should help. So the mass burned, okay, so the mass burned will give us the EH, yeah? And then the GFM will give us the enthalpy of combustion. Now, what you want to do is you want to remember that setup. So mass burned gives us EH, GFM gives us EOC, okay? If you can remember that, that makes this question 10 times easier, okay? So let's get back to my red pen. So we need to work at the GFM. So CH3OH. We've got 4 H's, 16 for the oxygen, 12 for the carbon, so that's going to be 32 grams. And I'm going to colour coordinate that as yellow, okay? And you'll see why. You'll see why. Now, let's go through this. Now, what do we have? Okay, now we have the GFM. The GFM is 32, so I'm going to colour that yellow. What else do we have? We have EH because we worked it out, so I'm going to colour EH pink. Okay, and what we're trying to work out? We're trying to work out the EOC, so we must have the mass burned. Okay, and what is the mass burned? Well, if we read the question, methanol, when 1.2 grams of it is burned, so the mass burned is 1.2 grams, okay? So that's the mass burned. Now, once we've got that set up, this becomes easy, okay? So we just sub the numbers in. So the mass burned, 1.2 grams, gives us EH, which is 27.17. And then the GFM is 32. And that's going to give us X. Yeah? So GFM is 32, the mass burned 1.2, and the EH is 27.17. Okay? So cross multiply, and then X equals 32 times 27.17 divided by 1.2, and what's that going to give us? 27.17 times 32 divided by 1.2, that is going to give us 724.5 kilojoules per mole. Okay? And I know what you're thinking, and I hope you're shouting at me. I've forgotten something. This is an exothermic reaction. So because it's an exothermic reaction, we symbolise that by making that a negative. Yeah? That means it's exothermic. And that's how we do it. Okay? If you can remember this, the mass burn goes to EH and the GFM goes to EOC, the enthalpy of combustion. This will make this question 1,000,000 times easier. Okay? Now, I'm going to do another enthalpy of combustion question. I'm going to do it with a wee bit of a twist, but you'll see that as long as we apply this, it doesn't make it any harder. Yeah? If you never had this, yeah, it would. But if we follow this, it's easy. So let's go through this then. Let's call this, well, B, obviously. So what I want you to do is well, not you, sorry. We're going to do it together. I want you to calculate the mass needed of ethanol. And again, I'll give you the formula, C2H5OH. So calculate the mass needed of ethanol in order to heat up. Obviously, we're burning the ethanol, okay? So calculate the mass needed to of ethanol to burn in order to heat up 200 centimetre cubed of water by 7 degrees Celsius, okay? Use the data book to help you. Okay, now use the data book to help you. Remember what I said, if the question's saying that, you need to use your data book, okay? So use the data book to help you. Right, change into red. Again, as we normally would, we will split the page into two. So EH equals Cm delta T here and enthalpy of combustion on the left. Yeah, do a wee sidebar. EH, we don't know. C, we do know, 4.18. M, we do have a mass. Remember the mass of water, yeah? So divide that by 1,000 to get into kilograms, 0.2. And then delta T, it's changed by 7 degrees Celsius. So EH is going to be 4.18 times 0.2 times 7. And let's do this. So 4.18 times 0.2 times 7. And we're getting 5.852 kilojoules. Okay? And I'll highlight it the same colours as I did last time. I'll highlight this pink. Okay? You don't have to highlight it when you're doing questions yourself. I'm just doing it just to show you how it all links in. Okay? So before we do anything, let's write a wee cheat sheet, I suppose. So mass burned gives us EH, GFM gives us the enthalpy of combustion. Okay, now what are we after? We're after the mass needed to burn. Okay, so I suppose we can highlight that. Yeah, now if we look at what we've already got, we've got the enthalpy of combustion. Okay, in order to get the mass burned, we need the other two. So the GFM, we can do that. We can work at the GFM. C2H5OH. That's 6 hydrogen, 16 for oxygen, and 24. That is 46. Okay, so I'll highlight that. What colour did I highlight last time? Yellow. So I'll highlight the GFM yellow. Okay, now the last thing we need to get the mass burned is enthalpy of combustion of ethanol. Yeah, but look at the question, it doesn't say anywhere what the enthalpy of combustion of. However, what does it say? It says use the data booklet to help you. Now, you should know that on the data booklet, the enthalpy of combustion questions are on page 10. Enthalpy of combustion values are on page 10. Okay, they're at the top. So that's the standard enthalpy of formation. We're after the enthalpy of combustion, however. Okay, so ethanol, that is minus 1367. Okay, so the EOC equals minus 1367. Okay, and finally, that's the missing piece of the puzzle. So enthalpy of combustion is 1367. Now, if we do that, all we need to do is sub everything in. So we're going to call that X because we don't know what X is. So X gives us EH, which we worked out to be 5.852. The GFM, we worked out to be 46 grams. Well, that's kilojoules. And the enthalpy of combustion, we used the data booklet, we found out that was minus 1367. Now we have all the pieces to work out the mass burned. So we cross multiply, and then x equals 46 times 5.852, and then divide the one that's connected to the x, we divide by, so we divide by 1367. Now you don't have to divide by the minus, obviously, because we're working out a mass burned, you're not going to get a minus mass. So we can take away the minus at that point. So it's going to be 46. So 46 times 5.852 divided by 1367, and our answer is 0.197. Now, what a lot of people do here is at the 10, they've got the blinkers on, they'll go for kilojoules per mole. No, because it's the mass burned. Okay, now because it's the mass burned, it's in grams, not kilojoules per mole. That's for EH and enthalpy of combustion. So for grams. Yeah, right. I hope that helps for enthalpy of combustion. I hope excess and percentage yield kind of just cemented what you already knew. And I hope this wee bit here really opens up your understanding to enthalpy of combustion. So if you remember that mass burn gives us EH, GFM gives us enthalpy of combustion. Okay, if you remember that, fill in whatever one you need, fill in the pieces to the rest, boom, easy. That's 3 marks just like that. Okay, right, that's us. I'll put up some questions for you to try on atom economy, enthalpy of combustion, excess and percentage yield. Okay, right, thank you.